All right, in a prior video, we looked at what the graphical interpretation of concavity is. Concavity is specifically in the context of what is the f double prime says, what does that say about f? And f double prime says about f, about whether or not the function f is concave up or whether or not the function is concave down. Right, so here's an example. Now let's go through this now and try to figure out the intervals on which the function is concave up and concave down and what that means. Excuse me. So here's a function f of x. Okay, that function is given in blue here. Okay. Now we know that if we look at tangent lines to the function f, tangent lines to the function f will tell us about f prime. Okay, so let's find f prime of x. Okay, so that'd be 6x squared minus 12x plus 6. Okay, and now we can see here that when we're looking at these tangent lines, can you see how that their slope is changing? So this is less sloped than the one before it, right here. This line has less of a slope. This one is less sloped than the line before it, right? So this slope is changing. The slope is getting less. So I think that the slope is decreasing. Okay. So what we're going to look here is at the rate of change to the rate of change. So we're going to create a gray graph here. So let's look at second derivative. And the second derivative is the rate of change of the derivative itself. And that rate of change is going to be 12x minus 12. Okay. So what we're seeing here is if we're going to create different sign lines, okay, what we can see here is that let's figure out where f double prime of x is equal to 0, aka we're finding a critical value of the function f prime of x. We're taking the derivative of f prime and setting it equal to 0. And we can create a sign line there for f double prime. And on that sign line, we're going to put a critical value of f prime, which is 12x minus 12 is equal to 0. And that happens, at x is equal to 1. So x equals 1 is our only critical value of the first derivative function. And when we put test points into this, okay, so let's take 0 and 2, for example. So when you find f double prime at 0, remember we're finding a sign line for f double prime, so we need to plug these values into whatever line this is labeled as. You'll get negative 12, which more importantly is a negative number. And we can see that f double prime at 2 is 24 minus 12, which is a positive number. Okay. And this jives with what we were seeing here with these slopes. We were seeing that the derivative was getting less and less slope. So the derivative, what this is saying is that f prime is decreasing. This second derivative being negative says that f prime is decreasing. But then the second derivative also had something to say about the function f itself. Right? So what we're seeing here is that this negative sign, if we look at the function f, and then we look at x is equal to 1, we know that when x is less than 1, because the second derivative is negative, that the function is going to be concave down, and when x is bigger than 1, the function is concave up. Okay? And then if we kind of coupled that with f prime, a sign line for f prime, we would see that this is equal to 0. The derivative is equal to 0. Also at x is equal to 1. F prime at 1 is equal to 0. So x equals 1 is also a critical value of f. And then if you plug in values, you'll see that the derivative is going to be positive and positive. Okay? So putting all this information together, okay, we can see that x equals 1 is a very important point in this graph. Up until x is equal to 1, we can see that the function is always increasing. That's because we found that right here the derivative was positive, so when x was less than 1. So the function is increasing, and the function right here it levels out, okay? But if you extend this graph a little bit further, you will see that the function continues to increase. Okay, so the function is always increasing. That's what the two positive signs are meant to be there. But we can also see that there is a sign line for f double prime, right? And that sign line for f double prime said that the second derivative was negative when x is less than 1 and positive when x is greater than 1. So let's go back here and look at this graph. When x is less than 1, can you see that the function is below its tangent line? The function is concave down. And then when x is bigger than 1, right, it's hard to see near the inflection point what's going on. But if you move a little bit further, you can see that the function is concave up. And that all jives with all the information that we were finding. This is the graph. 12x minus 12 is the second derivative. So the second derivative is negative. Function is concave down. First derivative is positive. Function is increasing. And at 1, that was a very special location. At 1, not only was the derivative equal to 0, but so was the second derivative equal to 0. So right at that point, the function will switch concavity and the function continues to be increasing. So that is an example of putting all the information together. We can say that we have an inflection point. There's a change in the sign of the second derivative. We have an inflection point at x is equal to 1. And we can now talk about the concavity of the function f, given what we know about f double prime.